Hi there, welcome to your lesson on binomial distribution. Notice we have here two paths, one to failure, one to success. There are two choices, therefore binomial distribution. Great lesson, let's get started. Let's begin with a little flashback on some things we've seen recently. First is the difference between discrete and continuous data. Discrete data is either data that can be counted, for example, the number of cars in a car park, or data that can only take specific values, for example, shoe size. Continuous data can be measured. For example, height, weight, and time are all continuous variables. Okay, so here's an example. We have at a coffee shop, there are 4 percolators, these machines for making coffee. Let's let random variable b represent the number of percolators that breaks in one day. Is this a discrete or continuous variable? It's definitely discrete because you can only have a certain number, a specific value of broken percolators. So what values can this discrete random variable take? Well, it can be, B can be 0 broken percolators, 1, 2, 3, or all 4 break in one day. So there's a set of possibilities and you can see it's discrete. Alright, let's take the coffee analogy a little bit further. Let's say we know that coffee bags weigh from 0.98 to 1.03 kilograms. Let's let random variable W represent the weight of a coffee bag. Is this a discrete or continuous variable? Well, W is definitely continuous because the weight can be any number in between these two values here. It can be measured. What values can it take then? Well, W can take any values between 0.98 and 1.03 inclusive, so we can show it like this. We can't list it like we did here, but we can show it's within this range of values here. Alright, so going on from there, again, B is the number of percolators that breaks in one day. There's our set of possible B values. We know that this is a discrete random variable, and we can represent the probabilities of each outcome in something called a probability distribution table. So here we have 0 broken percolators, or 1 or 2 or 3 or 4, and here's probabilities of each of those things occurring. So for example, the probability of there being 2 broken percolators is 0.06, and we can see it right here in the table. So again, this is a probability distribution table for a discrete data set or discrete random variable. It can be represented on a bar graph. Here's all the probabilities, and you can see the bars are not connected because this is discrete data. Alright, with that, let's recap something we saw a little bit further back, something we saw way back earlier in the course called combinations. Here is a combination formula. We sometimes say n choose r or n choose r like this, and we know that the formula tells us we have n factorial divided by r factorial times n minus r factorial. And factorials just mean multiply a number by decreasing values. If you go to consecutive numbers in decreasing integers, those are the multiplications you do. For example, if we had 5 choose 2, that would be written like this. 5 factorial following this formula over 2 factorial and then 5 minus 2 factorial, which is actually 3 factorial. Then again, factorial just means you multiply consecutive whole integers like this, and you have 5 times 4 times 3 dot dot dot. And on the bottom, 2 times 1, and over here this becomes 3, so 3 times 2 times 1, etc. We know when we have combinations we can cancel things. For example, 3's and 2's and 1's cancel. You're left with just this. That means 20 over 2, which is 10. So some combinations we can work out pretty quickly just by knowing how the rule works. Others we might need our calculator. But we also saw a very important connection between combinations and what is called, or what is known as, Pascal's triangle. We found out that for a certain row in Pascal's triangle, you can get every value in it using combinations. For example, if you did 5 choose 0, you would get 1, and that matches this value here. If you did 5 choose 1, you would get 5, which matches this value here. And if you did 5 choose 2, you would get 10, which matches this value here. So this would be 5 choose 3, 5 choose 4, 5 choose 5. Notice we start with 0, and we begin with 0 there. So that's an important connection we saw earlier in the course. We're going to use this now in this lesson, so let's keep moving ahead. Okay, so we are ready to talk about the binomial distribution. Binomial distribution models things such as this. For example, let's say we toss a coin 2 times and we are trying to attain as many heads as possible. So here is a tree diagram representing that coin toss situation. Here's the first toss, here's the second toss. And we can get either a head or a tail when we toss the coin, and then there's the same probability to get a head or a tail, 50-50, half or half. And then on the second toss, probabilities remain the same. Again, we can get head tail or head tail. Okay, great. This path on top leads to 2 heads, this one leads to head tail, this one leads to tail head, and this one leads to 2 tails. So that's something we've looked at in probability, but now we're going to take this and look at it from the lens of binomial distribution. Binomial distribution, for something to be binomially distributed, it needs to meet these 4 criteria, and they are: number 1, there is a fixed number of trials. And we can see that in our situation. The number of trials is 2. There are 2 coin tosses occurring. It can be 3 or 4 coin tosses, whatever, but there's a fixed number of trials. Great. Condition number 2, each trial has only 2 possible outcomes. So along each trial, so in this case each toss, there's only 2 outcomes, a head or a tail. And often in binomial distribution we call it a success or a failure. If it said we're trying to attain as many heads as possible, we can say head is a success, tail is a failure. So there are only 2 things that can happen, success or failure on each trial. Okay, great. Our situation meets that condition. Condition 3, the probability of success is constant. All right, so that means the probability throughout the trials, the chance of getting a success is always the same. And in this case, that's true. The chance of getting a head, which we're calling a success, is always the same. 50% chance here, 50% again. If we had more trials, it would be 50% each time. Constant. Great. Condition number 4, trials are independent of one another. What that means is, after you're done the first trial, in this case the first toss, the probabilities remain unchanged. There's no dependence. These probabilities don't depend on what happened here. If you got a head here, these probabilities are the same as if you got a tail first. That does not influence what happens next. Great, we meet those 4 conditions, so this coin toss situation is a binomial distribution. So let's get deeper into that now. So let's say again we have a fair coin tossed twice, which is what we just talked about. We're going to let x be the discrete random variable equal to the number of heads that are tossed in 2 trials of the fair coin. Use a tree diagram to represent this. Well, we saw that already, so here's the tree diagram. Now we're going to fill this probability distribution table. So again, x represents the number of heads, so this means 0 heads, 1 head, 2 heads. So what's the probability of getting 0 heads? Where is that path on here that shows 0 heads? Well, the 0 heads path is the one on the bottom because it leads to 2 tails, right? 2 tails means 0 heads have occurred. So what's the probability along that path? Well, if you multiply a half by half, you get 1/4. Okay, next, let's go to this one here. What's the probability of getting 1 head? Well, are there multiple paths? Yeah, in this case there are. The 2 middle paths lead to 1 head because this is head tail and this is tail head. So both of those lead to 1 head. So to find the probability of getting 1 head, you have to add the probabilities along both paths. So what is it? Well, that number is 2/4 because each path has a probability of 1/4, and now we have 2 quarters together, which is 1/2. And finally, what's the probability of getting 2 heads? Alright, clearly that is the top path. You multiply along those branches and you get a probability of 1/4. Notice these all add up to 1, as they should in every probability distribution, but also notice that in this case we have this happening. Okay, so there is 1 path out of 4 paths that lead to no heads, so we have 1 out of 4. There are 2 paths out of 4 paths that lead to 1 head, so we have 2 out of 4, and there's 1 path out of 4 that leads to that. But I want you to be aware that this idea about how many paths lead to there and that becomes our probability only occurred here because the probabilities are equal. It says 50-50. If these were not equal probabilities, we cannot simply count how many paths there are and say that's our probability. We would have to add up the probabilities along the paths, right? Okay, so let's keep going with this a little bit further. Let's see some important connections. So we have this coin tossing situation, and we know how many paths lead to each outcome. So how many paths lead to 0 head, 1 head, or 2 heads? Let's recap again. Okay, we know those numbers are 1, 2, and 1, right? One path here to 0 heads, one path to 2 heads, and then 2 paths to 1 head. That's what we just talked about. Great, that's how many paths we have. Now, what connection do you see to Pascal's triangle? So here's a bit of Pascal's triangle. Do you see a connection? Okay, I think the connection is pretty obvious in this case. We see these number of paths here, and they match this row in Pascal's triangle. This is not coincidental, and this is key to what we're going to be looking at here. So we see 1, 2, 1, 1, 2, 1. So row 2. Notice the number of paths leading to each outcome can be found in the matching row number. So we had 2 trials occurring here, so we go to row 2 in Pascal's triangle. 2 trials means row 2, and then we have all the possibilities here. Great. So let's keep going a little bit further with this. So now that we know that, what is the probability of obtaining 1 head? Well, we already talked about that in the probability distribution table, but let's look at it from the lens of paths again. So we can say there's 1 path leading to 1 head, there's another path leading to 1 head. Therefore, we have 2 paths, and each path looks like this. 0.5 times 0.5, which is a half times a half, right? So we have this probability times 2 because there's 2 paths, right? That's the same as adding those 2 paths. So that leads to this result. Notice the 2 paths can be written by a combination, and this is the key idea here. This is a combination. The combinations, we know, again, produce these values, right? This is 2 choose 0, 2 choose 1, and 2 choose 2. We know combinations produce these values. So we can say, well, if we need to figure out how many paths there are, we can just run a combination. This is a really big idea here. All right, so that works out to 1.5, which we already know. Half the paths lead to that situation. So here's the table we created before, and we can see that this matches what we have here. Okay, great. Good thing to see. Let's move on from there to a more typical situation, because it's very unlikely that when we're talking about binomial distribution that we'll have situations where the probability of success and failure are the same. So let's represent that using a biased coin. That means a coin where you don't have the same chance to get a head and a tail. So let's say we have this situation. Here's a biased coin tossed 3 times. 1 toss, 2, and 3 tosses. And notice the probability of getting a head this time is 2/3. And the tail is 1/3. So let's say now heads again is success. We have a 2/3 chance of success and a 1/3 chance of failure. So now it's a biased coin, and everything will change as a result of this. But the underlying ideas that we just looked at will remain the same. So let's take a look what we have here. First of all, how many paths lead to each outcome this time? And this time the outcomes are we can have 0 heads, 1 head, 2 heads, or 3 heads. So now we have an extra option here. Because of the extra coin toss, we can now end up with 3 heads. For example, on top here, head, 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 that's a path that leads to 3 heads. So what numbers go in here? In other words, how many paths lead to each of these outcomes with the heads? Let's check our work here. 1, 3, 3, and 1. So again, the 0 heads path is the one down here, because that's tails, tails, tails. And that means there will be 0 heads, but there's only one path that's like that leads to 0 heads. Every other path has at least 1 head in it, right? So we can say, and again, 3 heads, there's only one path like that. The top path there, head, 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 there's only one path like that leads to 3 heads. But altogether here, if we count the ends here, we have 8 paths in total. So we've counted 2 of them. That means there must be 6 remaining, these 6 middle paths. And these ones are either 1 head or 2 heads. And each of those has 3 outcomes. 3 of these paths lead to 1 head, and 3 of them lead to 2 heads. Hope you got the same numbers. Now let's check if that matches Pascal's triangle as well. So we saw a moment ago that row 2 showed us all the outcomes in the last situation. Now we're talking about 3 trials. So we're looking at row 3 right here. And row 3 we can see matches what we have here, which is amazing. All right, this is the very key here, right? The row tells us how many paths lead to each outcome. And again, these numbers here can be calculated using combinations. So we never have to look at Pascal's triangle to figure out how many paths. We can just say, hey, I can use a combination, and it'll tell me how many paths lead to that specific outcome. And that's going to be central in calculating probabilities. So what is the probability along the HTT path, the one where you have a head, a tail, and a tail? Okay, so you're trying to find the probability along the HTT path, so that's heads, tails, tails. So find it now. Okay, the probability is found by multiplying the probabilities along the branches. So you multiply 2/3 times 1/3 times 1/3 to get 2/27. Okay, next question. What is the probability of obtaining one head? Well, isn't that what we just found? We found the probability of getting one head. Oh, no, 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 but there's more paths that lead to one head, right? We found out there's 3 paths. So what's the probability of obtaining one head? Well, it is the sum of the 3 paths. Here's another one head path, tails, heads, tails. And here's the third one, tails, tails, heads. So those are the 3 paths that lead to one head. We can again see right here, 3 of them. Now, you can just do 3 paths times the probability we just found right here, which is 2/3 times 1/3 squared, right? So we're starting to create an important formula because again, we know this 3 paths can be obtained if we didn't have the tree diagram or we didn't have Pascal's triangle. How can we get this number? Well, again, these numbers are obtained using combinations. So we could have done 3 choose 1. That means row 3, or we have 3 trials, and we want 1 head. 3 choose 1. And then we know the paths look like this. Every one of the paths that leads to 1 head looks the same because all of them have 1 head, which is 2/3. All of them have a 2/3 in there, and all of them have 2 1/3, which are the 2 tails. Doesn't matter what order we rate these in, the paths all look identical. So we have 3 paths that look identical like this, and that's our full probability of obtaining 1 head. Now this brings us to our key formula for this lesson. It is the binomial distribution formula. And here's how it works. I'll show you now. So we can say a random variable, so discrete random variable x, like we have here. And this symbol means here it's distributed. It's distributed binomially, okay, binomially distributed with n trials. This shows you the number of trials and probability of success p. Okay, so this is how we write that something, a random variable, is distributed binomially. And here is the formula we're going to use, the one we just kind of came up with. It's going to look a little complex here, but we'll see it in an example in just a minute, and you'll see it's not complex at all. But basically, if we want to find the probability of some value for the random variable, then we do a combination multiplied by probability of success to that power, and then probability of failure to this power. Again, this looks a little strange or complex perhaps now, but let's take a look through an example. It'll make a lot of sense in just a sec. All right, so we had the example of tossing a biased coin 3 times we were just working at. Is that a binomial distribution? Well, let's check first because there's these conditions, right? Conditions of a binomial distribution are that there is a fixed number of trials. When we did the coin toss, did we have a fixed number of trials? Yes, we tossed it 3 times. Okay, next. Each trial has only 2 possible outcomes. Did we only have 2 possible outcomes on each trial? Yes, we did. Either a head or a tail. Great. Next, the probability of success is constant. In our biased coin case, the probability of success was 2/3, and that remained the same for every trial, so it's constant. Perfect. And number 4, trials are independent of one another. That means the probability does not depend on what happened before, and it doesn't. It was constant throughout. Perfect. So our situation is definitely a binomial distribution. Therefore, we would write it like this. Our random variable x, which means all the possible outcomes for how many heads we got, is binomially distributed, 3 trials, 3 coin tosses, and the probability of success was 2 out of 3. Great, that's how we would write that. And now let's do an example where we calculate that. So here's our tree diagram for that, and let's say we were asked to find this, the probability of 2 heads obtained when flipping a coin 3 times. So we want to know the probability of getting 2 heads. We could of course draw the tree diagram like we did, we could find the paths, multiply everything, but the whole purpose of the binomial distribution formula is that it allows us a shortcut. Imagine we had a giant tree diagram. We wouldn't want to do this by hand drawing it and calculating every path. So what we discovered is to find the probability of getting 2 heads, we found out first we need to know how many paths there are that leads to 2 heads. And we can find that by doing a combination. 3 trials, we want 2 heads. That combination will tell us how many paths on here will lead to 2 heads. And actually that is 3 paths. We can check it here. And then we multiply by what each of those paths looks like, right? So each of the 3 possible paths looks like this. If we're going to get 2 heads, we're going to have head, head, for example, so 2/3 times 2/3. So it's always the probability of success, and then how many times you want that success to occur is 2/3 to the second power, because there'll be two of those in your multiplication. And then if you have two heads, there must be a tail, so a 1/3. So that's the probability of failure here, and that's one of those in the path. So again, this tells us there will be three paths, and each of the three paths will look like this, where you have two heads followed by one tail, and the order of this doesn't matter. That is the binomial distribution formula that's going to help us. All right, so that works out to three paths, and each path looks like this, and therefore our probability is 12/27. It's that easy. It really is that easy. So let's try some more. Here's another example. On any morning, the probability that Sam takes a bus to work is 0.4. So let's say that's our success. He took a bus. Let's call that our success. And there's a 0.4 chance he takes a bus. Find the probability that in a working week of 5 days, Sam takes the bus to work twice. So here we're saying we're doing like 5 trials over 5 days. We're seeing what happens, and we're trying to see what's the chance that he took the bus twice. All right, so what we're looking for is, first of all, we have a binomial distribution. For sure we do, because the probability is set. There's a fixed number of trials. The probabilities are independent, and the other one was there's two options, bus or no bus, right? Okay, and we have 5 trials and a probability of success of 0.4. So there's our binomial distribution, and we are looking for a probability that he takes the bus or success happens twice. And you may be wondering, why doesn't he want to ride this bus? Why is there such a small chance he takes the bus each day? Well, the bus might look like this. It looks a little scary, so he takes it some days, but maybe he wants to avoid it. All right, so calculate it. Okay, using what we just learned, when we want to find out the probability, to avoid drawing the tree diagram and having to find everything on there, we just say, okay, 5 trials, 2 successes. 5 choose 2 is our combination. And then that tells us how many paths, and each path looks like this. 2 times taking the bus, and 3 times not taking the bus. And again, on each path, the order of these will change, but the numbers will be the same, because there will always be 2 bus trips and 3 non-bus trips. All right, so calculate that, and you get this value here. I hope you got the same answer. Okay, let's try another one. X is binomially distributed discrete random variable, which represents the number of successes in 6 trials. The probability of a success in each trial is 1/5, 1/5. What is the probability of exactly 4 successes? So apply the formula we just learned again, the rule, and see if you can get that. So we're looking for, first of all, here's our binomial distribution, 6 trials, probability of success is 1 in 5. So here we are looking for 4 successes exactly, so x equals 4. We do 6 trials, we want 4 successes, 6 choose 4. That will tell us how many paths occur, and each path again looks like this. 4 successes, so 1/5 times 1/5 times 4 times, and then 2 failures. 4/5 is the failure because it's the complement of 1/5, right? And that works out to, let's see, this is all worked out here, and we get this value here. Hope you got the same thing. Now let's look at this question, B. What is the probability of at least 1 success? So first of all, what does that mean? Write that as a probability statement. Okay, at least 1 success means this, greater than or equal to 1, because we want there to be 1 success or more, because it's at least 1. So 1 or 2 or more, etc. So we're looking for probability x is greater than or equal to 1. Well, that means we have to do this probability for 1 and 2 and 3 and 4, and that's too much work. See, that would mean having to find all these probabilities right here. Probability of 1 or 2 or 3 or 4 or 5. So you repeat this again for every one of those. But that takes a lot of time, right? What's the one value that's missing here? The one that's missing is probability of x equals 0. So can't we just do a complement like this, right? We learned this in our probability unit. 1 minus the probability of that occurring is actually the same as the probability of these occurring. So let's simplify it. Let's do this. Okay, so try that now. 1 minus this. Okay, let's check our work. So 1 minus that probability. Here's that probability. 6 trials. We want 0 outcomes to be a success. So here 1/5 to the 0 power, because along that path we have 0 successes and 6 failures, and we get to this final answer when we subtract from 1. Okay, great job if you came up with that. Let's keep going. So next situation we have is this. A drug is known to have an 80% success rate for people using it being cured. A medical testing program administered this drug to 2 groups of 10 patients. Find the probability that all 10 patients were cured in both groups. For this one, it's a little bit different than we've seen so far. I want you to begin first by ignoring the fact that there are 2 groups that were given this drug. So just concentrate on one group of 10 people, and we want all of them to be cured. So here's our success rate. We want all 10 people to be cured. Find that first. Okay, let's check our work. So the probability that the success is 10 choose 10 and then 0.8 to the 10th power, because along that path we have 10 successes, 0 failures, and that works out to this number here. So now how do we take that forward to, okay, that's the probability of success across 10 people in one group, but now we have another group where we're going to have 10 people and we want full success. So think back to what we did in probability with that. We want something to happen and then something to happen again right after it. Okay, so to deal with that in probability, we just use the intersection symbol, right? It means and. So we're finding probability of there being 10 here, and then probability of 10 successes in the next trial as well, the next trial of people. So we're just multiplying those two things by each other. Or you could just say you're taking this and squaring it. It's the same thing, multiplying or squaring, and you get this value here. So I hope you see the logic behind that one. Let's keep going. Here's another one. We have a binomially distributed variable with 6 trials and probability of success 1/5. What is the probability of exactly 4 successes? So begin with that. First, we'll write out the binomial distribution. It looks like this. So random variable x is distributed binomially, 6 trials, 1/5 is your success rate or probability, and now exactly 4 successes. What's it going to be? It should look very familiar. We just did a moment ago, so I'll share the answer again. So exactly 4 successes was this, right? We just put x equals 4. But let's look at question C here. What's going on here? It says, what is the probability of 3 or fewer successes? How would you write that as a probability statement like this? Well, that would look like this. 3 or fewer, so x is less than or equal to 3. And what that means is we're actually looking for a probability of 3 occurring, or 2 successes, or 1 or 0. So there's all these options, right? We're looking for probability of 3, which would be calculated like this, right? 6 trials, 3 successes. Here's a success, 1/5 is 0.2, and here's 3 failures, all right? So 3 successes, 3 failures. All right, the next one then would be x equals 2, right? Because we're looking for anything under than 3. So we need this one. What would this one be? Well, that one would work out like this, which would give you a probability that we found, and then you need 1, which works out like this, and then you need 0, which works out like this. So this is a lot of work. You have to find each probability of each value and then add them all up. That's a lot of work. So your natural question might be, is there a quicker way? There must be, and there is. So let me show you that now. Now that we understand how the binomial distribution works in terms of the formula and how these paths work and all that stuff, let's now grab our calculator and find a way for our calculator to do this for us. There's something called Binomial Cdf and Binomial PDF that helps us with this. Let's do that now. So here's my calculator. Here's how we're going to do it. So first of all, let's do the one where we have 4 here. For that one, we're going to run a binomial PDF. PDF means when you're looking for one single value. And CDF, the C means cumulative, and that means when you're looking for many probabilities added up. So let's do a PDF for this one. So I'm going to press on, we're going to press second, and then vars. Above that we have distribution here, so distribution. And down this list, we have to go down the list to find binomial. And when I go down, I can see, here it is, binomial PDF and binomial CDF. Again, when it's a single value we want, we go to PDF. So I'm going to go to PDF, here, enter. And trials, well, we're running 6 trials in this situation. P-value, probability of success, is 1/5 or 0.2, but I'm going to put it in as 1/5. And X value, what is the number of successes we're looking for? 4. Great, let's see if that value matches what we have. Paste, enter, there's our answer, 0.15, and I think that matches. Oh, it's covered up now, but it does match what we had here for sure. Alright, so we just confirmed that binomial PDF gave us this same value. Now let's check the other side. So let me get this calculator again. And now we're going to check if we can find this one, because this is the one that was really time consuming to find each of these individually. So let's use our binomial CDF this time. Again, CDF means cumulative. So second distribution. I'm going to go up this time to find it quicker. Binomial CDF is right here. Cumulative, that means I'm going to find all these accumulated. Enter. Trials, we're still running 6 trials here. The probability of success is 1 out of 5. The X value, we're running a CDF, and the way CDF works is you give the upper value and it will give you the sum of all the probabilities from that value you enter and below. It will always go from that value and below. So it's doing exactly what we're doing here. It's going to add all these up here. Okay, here, enter, and it's going to give us an answer. 0.98 probability, very high probability, and that would be the sum of all these as well. Great, you've learned how to use the calculator. Let's use it in the next problem. So this is an exam style problem taken right from an old exam, very much a binomial distribution problem. Let's see if we can solve it one by one. It tells us a factory makes calculators. Over a long period, 2% of them are found to be faulty. A random sample of 100 calculators is tested. Part 1, write down the expected number of faulty calculators. Expected number. We learned a formula last time called the expected value formula. How would you apply that here? Okay, to do the expected value, we just do the number of trials, which is 100, times the probability of failure or faulty calculators. So multiply that, we are expecting to see 2 of these calculators to be faulty. Okay, part 2 or B. Find the probability that 3 calculators are faulty. Okay, so now we are running a trial of 100 calculators. We know the 2% are faulty and we want to see that 3 are faulty. So run your binomial distribution on that. You can use your calculator, but set it up as a formula first. Okay, here's what it should look like. We are looking for 3 faulty, so x equals 3. And yes, faulty things are not a success, but in this case we'll call that the success because we want 3 of those things to happen. So 100 choose 3. The combination will tell us how many paths lead to 3 faulty calculators. Okay, so the 3 faulty calculators, this is the probability of 1 faulty one, and then that means the remaining 97 are not faulty, which is a 0.98% chance if this was 0.02. Alright, that works out like this. Again, you could have run your binomial PDF on that and it should confirm the same number here, so test it out. Okay, final problem. Find the probability that 5 or fewer calculators are faulty. So again, 5 or fewer, that means 5 are faulty, or 4 are faulty, or 3, or 2, or 1, or 0. So you can either run this 6 times, 1 time for 5 and 4 and 3 and so on, or you can run your CDF, binomial CDF on your calculator. So try that now. Okay, running the binomial CDF using 5 and under, we get this value here. So double check that you got the same one. Okay, last problem we have here for you. Thank you for hanging in there. It's been a long video, I know. So in the mass production of computer processors, it is found that 5% are defective. So just like the calculator thing, we have some defective parts in production. Processors are selected at random and put into packs of 15. Okay, if a pack is selected at random, find the probability it will contain 3 defective processors. Try that now. You can set up the binomial distribution formula and then run a PDF on your calculator. So here's the answer for that first one. This is definitely a binomial distribution. 15 trials, 15 processors in 1 pack. Chance of a faulty one is 5%, which is 0.05. We're looking for 3 faulty ones in the pack. There's what our binomial distribution formula will give us. 15 choose 3, 3 faulty, 12 non-faulty, and then that works out to this. If you ran a binomial PDF, you should get the same answer. Next one, no defective processors. This time we're running probability x is 0, and you should get this value here. Again, you could have done that with PDF, binomial PDF. Okay, next, there are at least 2 defective processors. Look at that wording carefully. Okay, 2 defective means x is greater than or equal to 2. That's different what we've been just doing. We were looking at ones where we're some number and under, but now we're looking at some number and above. So what will that look like if you write it as a complement? Okay, you would have to write it like this. 1 minus probability of x is less than or equal to 1. Because if you're looking for 2 and greater, you want to find the probability of 100% minus 1 or less. It's easier to calculate 1 or less than to do 2 or greater. But not only is it easier, also on our calculator, when we run a CDF, the cumulative binomial CDF, it always does the number we put in and under. So if we had run a CDF with 2, it would have calculated like 2, 1, and 0, but we want to go above 2. So we're going to do 1 minus this. Let's calculate that now. Check your work. Hopefully you got this number. Again, make sure you really pause and understand the logic of this setup here. Okay, it's definitely time to wrap things up. One last problem. It's the same problem continued with a little bit more on it. So check it out. Now we're going to here, same problem. These are the questions here. Now we have 2 packs are selected at random. Find the probability there are no defective processors in either pack. So you're looking for x equals 0, but across 2 packs. So this is kind of like that drug administered in testing problem that we did earlier. So check your work here. We're looking for 0 in one pack and 0 in another pack. So you're finding second problem looks like this. At least 2 defective processors in either pack. So again, we calculated 2 or more. So 2 or more and 2 or more defective in another pack. So we're going to use the numbers from the previous problem that we solved, right? And the third situation here, no defective processors in one pack and at least 2 in the other. That means no in one pack and at least 2 in the other, or we can reverse the order. At least 2 in the first pack and no in the second pack. Remember that. We can reverse that. If you remember back to probability, we did this often. Calculate all 3 of those. You get this, this, and this. Check your work carefully. This was one of the tougher problems we've looked at. So great job. We will see you soon to do more together.